Professor Ivan Habernal holds a full professorship for Fairness and Transparency at Ruhr-Universität in Bochum, Germany, which is his position there is jointly affiliated with the Research Center Trustworthy Data Science and Security. His current research areas include privacy-preserving natural language processing, legal NLP, and explainable and trustworthy models. His research track spans argument mining, computational argumentation, crowdsourcing, large-scale corpora, serious games, sentiment and sarcasm on social media and semantic web. And as you can see in the background, he's also a musician. So if you have a lot of extra time, he promised he'll do some music.
Okay, thank you very much. So I have to say, let me share my screen, because if I don't say it, it won't work. That's what I've learned on Zoom over the years. And I have to ask also, can you see my screen?
We can see your screen. Yep.
Awesome. So let me start. So thanks for the invitation. I'm really happy to be here virtually. Okay, so I'm going to talk about people, language models, and privacy. And this is a privacy week, so I don't think we need strong motivation here. But let me just give one time little motivation. So it's been like a year ago when it was in the news again that ChatGPT is leaking training data, violates privacy, and it remembers something and things like that. So for us, researchers and practitioners in the field, it was nothing new. And I found this paper actually pretty cool. So it has some usual suspects as authors. So Nicholas Carline, for example, and other Florian Trammer, other people, Catherine Lee, who actually started prompting ChatGPT. And if the prompt here was that repeat this word forever, poem. And if you prompted ChatGPT, it's just starting spitting out the training data. And everybody was, oh no, it remembers the training data. Of course it does, because that's how it's trained. And it remembers something. So there were a couple of papers on that. And this is the motivation why privacy is important and why should we be dealing with privacy in language models. So what are we going to work with is a formal guarantees of privacy in this talk. So I don't know how much you are familiar with the concept of differential privacy in the crowd. I'm assuming in this context, you might have some knowledge about differential privacy. So I'm not going to be very mathematical today, not at all. But here's one example, one sort of definition of differential privacy, which is basically showing if we have two data sets and they differ in one person's entry here, so they are called ages and inputs, then any algorithm which is run on this data set or the other data set, their differences are probabilistically bounded, which means, if we observe a X here, then we cannot really tell whether it's coming from the database D or the database D prime until, up to this factor of epsilon, e to the epsilon. So there's some bound on this likelihood of these two things. So this is the important definition. So whichever algorithm with differential privacy we're using, we have to make sure that it will work no matter what happens with the notion of if I remove one person on the data set or replace this person in the data set, the results of this algorithm will be mostly similar. So how can we transfer this to working with language? Because this is what we've been doing in my group, so natural language processing. So we have this idea, okay, so we can actually protect each individual single text of a user by trying to rewrite it. So we can take a piece of text, which kind of might be maybe asking, what is the flights from New York to Washington tomorrow? So this is one of the particular data sets we are working with, and try to rewrite it to something similar, which would keep the sensitive information intact with these differential privacy guarantees. So we built a model called DP-BART. So it's using one of those so-called transformer models for rewriting. I don't think the details actually matter here, but we are showing the trade-off between the privacy and the private models for rewriting and the non-private if we take this rewrited samples and do some maybe classification on top of those. And we are showing a couple, we are overpassing the state-of-the-art models, but the main takeaway message is that, the trade-off, we see these epsilons here on the x-axis, and for epsilon of infinity, which means non-privacy, we get some results down the road. And if we make the epsilons smaller than infinity, like 100, we lose something on the performance. But if we, if we tweak down the epsilons more, the lower the epsilon, the more the privacy, so to say, in this DP world. So for very low epsilons, we get almost no results, so bad results. So this is this trade-off between how private can we be formally and how usable or useful this data set is. And anybody working differential privacy here, if you see epsilon of 100, you might be asking like, really? Like, are you serious about epsilon 100? And that's true. So are the results actually useful? I mean, on a paper, it works, but epsilon of 100, does it mean any privacy? And the answer is actually it doesn't, because of these bounds. So e to the epsilon, e to 100 is just a very huge number. So basically you have no distinguishability or indistinguishability between any 2 points. And basically you will reveal everything in the sensitive data. And we also ask people what they think about epsilon, which epsilons are good for differential privacy, and whether, will you give me your data if I give you differential privacy of epsilon, I don't know, 10,000. And the truth is, and this is, by the way, a very nice joint paper also with Frauke, that users do understand implications of giving their data under this differential private framework. And roughly, depending on the scenario, which kind of data, so we had a couple of different scenarios here, but anything over 4.5 or 5, epsilon of value 5, we have no chance of actually getting people give us our data. So this is a signal saying like, okay, if we do something very serious with differential privacy on any of those data, we have to make sure that the epsilons are actually low enough, like under 5. So which means everything I was talking about here, like rewriting with differential privacy guarantees, well, it won't fly. It won't work in the real world. It's impossible. So the second question, okay, so can we do something else? Can we move from rewriting one piece of information into another to this notion of, let's say, centralized or global differential privacy? And in this case, we have somebody who is a trusted curator, and it's collecting data from multiple people, which, they trust the curator. And then there's somebody else, the Bob outside, and he's asking some queries. So running a function on the database, and we can return the true answer, or in differential privacy world, we would noisify it. So add some randomness to the answer. And the idea would be then again, that if we have two data sets, then in the second, on the right-hand side, we remove one person from the data set. Then the result of these queries would be probabilistically similar. So there will be some differences, but in general, in probability distribution, there will be some bounds, how they much differ. So this is how we protect privacy with differential privacy. So can we utilize this for doing some, let's say, machine learning? And the answer is actually yes. So typically, when we are training neural networks, so this is this, go-to model these days is neural networks. We use the so-called stochastic gradient descent, which is an iterative algorithm and takes a data set. So here we have Alicent and Julia on the left-hand side. And after querying the data set over and over and running some function, which could be a classification or something else, we end up with a model, and the model is in a way like a bunch of numbers, bunch of parameters, which we train on this data set. And while doing this iterative updating, we just update so-called parameters iteratively. So the numbers in the model, the weights. Okay, so far so good. So we could actually use this thing in this iterative training. And since we are asking each of the updates, we're asking something about the data set. If we privatize this question, so to say, this query with differential privacy, we should end up with differential private model. And this is exactly what people have been using since, let's say, 2015, 2016. So the idea is that we can train on a data set which contains private information of people with the standard stochastic gradient descent. And at one point of this stochastic gradient descent, we just inject some noise in there. And if we are good mathematicians, we can formally calculate how much noise we need to add to keep this differential privacy guarantees. So this has been a go-to kind of method for protecting any data in machine learning if we want to be serious about privacy of your training data. So far, so good. So can we use this to work with texts? I mean, of course, we can use it for classifying text. So if these documents were text and we want to classify them into some classes or sentiment analysis and things like that, we can do that. But we can do even more. So one idea could be, can we generate texts by training a model, so-called fine-tuning a model, with these differential privacy guarantees, and then use this trained model And because we know everything is in the model is protected already, we can try to generate text out of this model, which would be synthetic text and also wouldn't leak anything from the training data. So we do here a couple of data sets and fine-tune a model on that. So let me just give an example of a data set. Could be a spam email. So then we would prompt the train model asking, oh, please write me a spam email. And then the generated output would be something which is privatized, synthetic, but should be close enough to the original data, because we want to use this text for some downstream tasks, such as classification or learning something else. So we took this data set and tried to generate a couple of data. And this worked actually pretty good as compared to this local differential privacy rewriting, where we end up with epsilons like 100. I mean, training models and generating data from models, we can get to epsilons of 3 or 8. So this is really an achievement, as compared to these huge epsilons, because it's using a different notion of differential privacy, a little bit, this central one, but still it gives useful results. So if we compare it here on this, we try different models, but the upshot here is that for epsilon of 8, we actually get pretty decent results with one of these language models in generated synthetic text. So this is really pushing the epsilons down to something usable, which is great. And I'm just going to show a couple of examples that the models are generating. I hope it's readable. But just to show that some models are actually super struggling with this noise. So on the left-hand side, we have no privacy, and then some models are producing text, which is kind of makes sense. So this was a data set about app reviews, which are considered sensitive in this use case. And you can see that the text is actually fluent. It makes a lot of sense. So we can use this down the road. And if we go down with epsilons to 8 or to 3 on the right-hand side, then some of these models actually are producing something almost nonsense, like, I'm happy you like the game, or Nguyen, 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 or some very short nonsense sentences. So the trick here is now, and the open question is like, how, can we improve these model generation under this so much noise? But it turned out to be very useful. So I'm super happy this paper just got accepted to the North American ACL just 2 days ago. So you can check it out. So when we go from generating synthetic data, we see that we can also work with privacy and other contexts. And here there is one context about machine translation, because there are data sets, if we want to train a machine translation model, that can contain sensitive information, obviously, like internal company data, for example. So what the community is typically using for machine translation are corpora, where we have the training data in form of sentence aligned. So we have one sentence in one language, English, for example, and corresponding translation in German. And these are broken by sentences, and we assume these points are independent. Well, then the trick is the devil is in the detail, because the independence is going to be very important for the rest of the talk. If you look into real data sets, for example, there's one called business meetings dialogues, where it's a fake business meetings in companies, and then we have the pairs here. So the customer is saying, well, my name is, for example, Imo Hande Hornig, and there's a couple of conversation, and then another pair of sentences is Agent O, are you, and so on, are you the Imo Hande Hornig, which means the name of the customer is present in the whole dialogue in a couple of places. If we take the standard approach to machine translation, we would cut this dialogue into sequences, and then if we train this with differential privacy, we could kind of pretend these are, different examples and these are independent. In fact, they are not. I mean, this is coming from a long discourse, so we need to do something about it. And we did some experiments here in this paper. What happens, for example, how much you can reconstruct from models trained on sentence level versus document level. But the only way how to properly deal with this is to go to the document level translation. So we need to take the whole discourse, in consideration as one training example, but everything then becomes very complicated, because document level machine translation is not really existing so far. There is some research on that, but not that much. And of course, the performance really drops with this long documents. So if we compare it under some meaningful epsilons, like 10, if this is still acceptable to some, then the sentence level translation works. On the document level, it's just basically nothing. So the blue score, the higher, the better. And it doesn't work. So this is our last year EMNLP paper on this exploration. So this was machine translation, but let's move to the actual large language model. So, just to understand what we mean by a large language model, it's many things, but under the hood, it's a probability function. So we need to estimate the probability distribution over all tokens in our inventory given the preceding tokens. So for example, you heard the sentence, so I was at this party at Joe's place last night, but man, I was so tired. So like at about midnight, I said, Joe, and then leaving out, calling it a night, gonna head home and stuff like that should have some high probability, and the other, hungry or in love should maybe have like lower probability. And this is basically what language models are doing. They predicting the next word, so to say. So how does privacy, and in particular differential privacy, being solved in language models? Or so there are some papers on that, and actually one of the early ones is from 2018 from Brendan McMahon and others, where they apply differential privacy to language models and how they deal with this this notion. Because in differential privacy we work with sort of like tables. So each row corresponds to one person. You remove one row, you have the neighboring data set. Here they said, oh, you know what? Of course, I mean, there is a user who might be typing multiple messages, and we just want to make sure that none of those messages is going to be leaked. So we're going to remove all users' messages, which means if we have one data set with all users and one data set minus all the messages from my users, these are our adjacent data sets, and then we can use the formal definitions of differential privacy to train on this data set. So far so good. Then you start looking into details, and what they actually they experimented on is Reddit. So they used some large public data set on Reddit posts, and then the cited paper actually say, oh, we extracted 2 billion comments that were posted on Reddit. So this is never stated, but my assumption is here that they just took all the comments from the user from the discussion threads. So basically, if a user posts something in a thread and then there's a reply and then there's a reply and then the user again, they took it, which means there is some dependence between two posts of one user, and also dependence between what other users are writing. So remember, dependence and independence, we'll come to that. But anyway, I haven't seen any paper criticizing this paper, so I'll take it like that. Maybe there's a room for some criticism, maybe not. But it seems like privacy in language model is not a solved, it's an open question. It's not solved, because here's another very cool paper by Hannah Brown, Catherine Lee, Nilofar Mirzgalach, Reza Sokri, and Florian Tramer. I really highly recommend reading this paper, because they're showing what happens if you just if you pretend you're doing this neighboring data sets by removing data. So here there is a conversation between two persons. Hi, Alice, how are things going? Oh, not great. Yeah, I'll already tell you I'm getting a divorce. No, I'm sorry to hear that. What are you going to, and stuff like that. So now if we take the Brendan McMahon's et al. Approach and we just remove all messages from Elise, well, the thing is that on the right-hand side, from the last message, we can kind of infer that the person, we are mentioning custody of the kids. So it means we are really doing something with a person, even though Elise's data are just out of the database. So there is some leakage of the data, and we should take it into account. So that's kind of tricky. Is there another solution? Well, maybe we can just remove all the conversation from the data. So there's no conversation between Elise and Bob. But who knows? Maybe in between, Bob talked to Charlie, and Charlie said, hey, Bob, how are you going? Oh, pretty good. How are you? Oh, did you hear Alice is getting divorced? So when the secret leaves the person, you have no control whatsoever. Can we fix that here? Well, I don't know. So the question is, and I promise, this talk will be about questions and fundamental puzzles. So the question is it a fundamental problem? So the text in most corpora that we use for training LLMs, or anything like in most corpora, what text is about? So it has like some coherent discourse. It's usually causal. It goes like left to right, and past go to present and to future. There's some long-range dependencies in texts. There are also dependencies between documents on the internet, of course. And on the internet, which is the corpus for training data, the past influences the present. So whatever we wrote before is there, and we're gonna write afterwards. So there's, there's some very much, it's very connected. And which means there's some unrestricted flow information. So the fundamental question here to ask, what happens if you randomly chunk the web in blocks of 1,000 words long and pretend they are independent? That's gonna cause troubles. I'll finish in 1 minute, okay? Good. So how about the independency of rows in differential privacy? So there are some major assumptions, but if you really go deeper into the original research, I found this one of the early papers from Arvin Bloom's into that work and other co-authors. And they're actually saying these have to be independent. The rows have to be independent, because if you can infer information in one row from other rows, then you have problems. And this is extremely important, but usually violated assumption, and that's a problem. So can we, address independency of rows? Well, we have to make sure that all the examples are mutually independent. And the fundamental question, how can we measure, evaluate, guarantee that any text snippet A is independent of text snippet B, because we're working with, web corpora. And even if this is possible, can we scale this? I don't know. I don't have any answers to this question, but let me just do like back of the envelope calculation. So let's say we have the context size of language model is 120,000 tokens, which is Llama 3. It was trained on 15 trillion tokens. So we would have roughly, by chunking, 120 billion examples. So we would need to compare 8 to the power 8 times 10 to the power of 15 pairs of chunks and decide whether these are independent or not. This is when we can be sure that the independence assumptions are met, and we can use this data set for training a large language model in order to satisfy not violating differential privacy by the design of the database. So formal differential privacy in language models, I believe it's theoretically possible, but maybe practically infeasible. And if this sounds like an interesting research, I'll be happy to talk and happy to address any questions or concerns you might have. So thanks a lot.